go. All right, Sasha will give his third talk.
All right. Yeah, so today, hopefully we'll finally get to the gist of this p-adic Riemann-Hilbert functor families, so over actual geometrically interesting varieties. And then hopefully tomorrow we'll do some technically lighter applications of this. We'll connect it to some more classical notions in Hodge theory. So let me today we almost completed the picture for what happens over a point. So it's actually completed. So what we were studying, so we had this p-adic field, and I defined this functor h from QP representations of its Galois group. And that was valued simply in vector spaces over this field K infinity, equipped, so let's say I'll call them M, equipped with a single operator. And so what was this construction? So it was mimicking the construction, it was kind of we were trying to compute something very similar to this Diderot functor, but then we stopped at the intermediate step. So we tensored our representation V with this field C, and we took invariance not for the whole Galois group, but for the kernel of the cyclotomic character, right? So let me remind you that K infinity was this p-cyclotomic extension. HK was the Galois group of K bar over K infinity. And gamma K was the quotient of the whole Galois group by HK. So now it's just the Galois group of K infinity over K. And via the cyclotomic character, we viewed this as an open subgroup of Z plus. So thanks to this surprising almost purity statement, we noticed that this was a vector space over completion of this field K infinity of the same dimension as V was. And more specifically, we said that we could decomplete it in that there is actually a vector space over this algebraic extension of K. And then, well, this was a completely functorial procedure, and there was still an action of the group gamma K, right? So there was a residual action of gamma K here. And then it was just, this action was K infinity semi-linear, and it was just my choice, maybe it's not necessarily the most fundamental step in this story, to trade this action of gamma for a single linear operator, which was defined as the derivative of this action of gamma. So it was the limit over elements of this Galois group converging to 1 of these values. And right, we remarked that this was a well-defined, literally linear operator in K infinity. So this passing from this gamma K to phi, it loses a little bit of information. For instance, if gamma was acting through a finite quotient, phi would just be 0, because eventually gamma phi would be equal to V. But for our purposes, this is a harmless thing. And somehow thinking of this gamma equivariance in terms of this phi makes the picture a little more uniform when we'll talk about relative situation. But otherwise, you should think of this phi as just packaging the action of this one-dimensional Galois group. Okay? So let's just do an example of how this looks like. So our favorite example of a power of a cyclotomic character, where A was some p-adic number, again, such that which was close enough to 1 so that this power made sense. So then what will happen when we compute this functor? So fortunately for this very specific choice of a representation, this first step of figuring out that invariants under HK were a vector space of a large enough dimension, this is completely trivial, right? Because the action of HK on this representation is trivial. So V tensor C HK. So let me choose a basis element for this V. I'll call it E. This is just spanned by E tensor 1 over invariance in C, which is just the completion of K infinity. Okay? And now, well, there's this H of V was the maximal K infinity subspace, right, it was the maximal finite dimensional K infinity subspace in which the Galois group still acts. And here it's simply spanned by this K infinity without the completion. And so how does this phi look like here? So let me do this computation here. So what will happen if I try to compute phi of E tensor 1? Well, I have to act on it by elements of this gamma k, which just multiply them by the eighth power of this economic character. So this will be the limit as gamma goes to 1. So I'm trying to derive this, to take the derivative of this section. So it's Heights economic of A of gamma minus 1 over the first power of this economic character of gamma minus 1. And this is just scaling this element E tensor 1. And, sorry. Let me give myself some space. So notice this is just a derivative of the eighth power function, which I evaluate at 1. So this limit is just A times E tensor. Okay. So I've got so this operator just multiplication by A. Okay. So I traded this economic character for this vector space of an eigenvalue which remembers the power of the character. Okay? But again, somehow this was really especially rigged so that the basis in this vector space was easy to compute in terms of the original representation. For arbitrary color representations, this will be the most interesting stuff. And let me introduce the notation. The notation in general that eigenvalues of phi acting on H of V are called Hodge-Tate weights of my representation. So the motivation for this is that, as Alice explained to us, if V was cohomology, say, of a smooth proper variety, then if we tensor this representation with C, then this would be isomorphic to the direct sum of Tate twists, where the multiplicity spaces are Hodge cohomology groups, where this is just the minus I power of this economic character. And so now if we completely understand V tensor C as a Galois module, we can just run this computation, and you see that now, thanks to the hard work and interesting periods which go into this isomorphism, this representation V tensor C looks as if the original V was just a direct sum of its economic characters, right? And then it's just a general computation as what we did here, and so we can just work out that H of V in this case is the direct sum of these groups. Well, with scalars extended to K infinity. In general, there is not a canonical K structure on this. But now, on this Ive group, phi acts by minus I. Right? Because of this minus I split over here. And so you see that eigenvalues of this operator, they remember the multiplicity of the eigenvalue I remembers the Ive Hodge number. Okay. Well, so far, if you like, this was there are many different linear algebraic ways of packaging the Hodge-Tate decomposition. Okay, but now, experience shows that we also it's more interesting to consider periods not just valued in C but in B to run. This is really the object we want to work with, and I'll emphasize that this kind of adds a structure which, especially in the relative case, which is not visible otherwise. So I'd like to write down an analog of this functor, which I originally advertised as the Riemann-Hilbert functor, where I work with Petrov instead of C. So, okay, so what was happening here? So I have H of V was a decompletion of V tensor C. Now, what we actually are interested in is the functor d de Rham. So let me instead consider v tensor b de Rham, or especially let me consider v tensor b de Rham plus. Okay. And let me try to do the same computation for it. So as we discussed, b de Rham plus it has a filtration whose associated gradients are just Tate twists of C. And so on associated gradients, the action of HK is just the same as for C. So let me maybe remind you that. Let me remind you this thoroughly. So I don't think we've quite discussed this, but Alice, maybe you can correct me if I'm wrong. So how does this b de Rham plus look like exactly? So there was a filtration which Alice defined, but let me think about this filtration slightly more explicitly. So I claim that in b de Rham plus there is a canonical element T. Oh, sorry, canonical up to a choice of compatible system of recipes unity, such that any element of the Galois group acts on T via this economic character. Right? So in terms of the description through A infant the tilt, it's not hard to write down formula for this T, but just maybe to get some additional experience with these period isomorphisms, let me quickly show that if you believe that de Rham comparison, then you have to believe that there is a choice of such T in b de Rham plus. And this T is actually a period of some particularly simple Galois representation. So let me write down the p-adic comparison isomorphism for the projective line. So suppose that my variety was P1 for K. Then, well, it's interesting, homology is in degree 2. And so I know that second italic homology, tensor b de Rham, is isomorphic to second de Rham homology, tensor b de Rham. Right? And this is compatible with the Galois action, where here the Galois action is the tensor product action, but on the right, this is just the Galois group acts only at b de Rham. So it's very simple as a b de Rham Galois representation. And now, well, by serduality, the second de Rham homology is canonically identified with the base field K by the trace. So this standard product is over K. So there is a canonical element 1 here, which is stable by the Galois group. And so it has to get carried to some element here, which is stable by the Galois group. But how does the second italic homology of P1 look like as a Galois representation? Well, it's the action here of the Galois group is not trivial, rather it's the inverse of this economic character. So the element 1 in here gets carried to a Galois invariant element in here. But the Galois invariant element in this tensor product is the same as a map from QP of +1 into b de Rham, which is Galois covariant. And specifying, well, if you choose a generator in the state twist, then the image of this map will be exactly T. Okay, so this 1 gets carried to, well, a generator here, which will, again, confusingly equal 1 tensor T. And you can check from the compatibility with filtrations that this T will lie in b de Rham. Right, so there is this canonical element, and in terms of this canonical element, the filtration on b de Rham plus is defined. So the filtration on b de Rham was just shift by powers of T of the b de Rham plus. Okay. And it's not a poor choice of notation that my T is the same as the T which appeared as a coordinate in my formal disk, as you will see in a second. So suppose I'm trying to study the functor d de Rham, and as an intermediate step, I've taken invariance just under this Galois group HK. So I claim that this can be similarly decompleted to an object form RH plus of B, which is what I was after. Tensor. Now, well, what kind of module is this? Well, it's a module over the invariance under HK in this ring b de Rham plus, which is something. But the claim is that it's still filtered such that the associated gradients are invariant in the associated graded pieces. And whatever it is, I claim that its decompletion is, well, there is a, sorry, there is a natural map from k infinity double bracket c into beta 1 plus, because, well, k infinity does map into beta 1 plus. And then t maps here by my choice of an element. And since beta 1 plus was a, well, first of all, t does land in invariant because the Galois group acts on t through this economic character. So kernel of this economic character acts trivially. And then beta 1 plus, as Alice explained, it was a complete ring with respect to the filtration which is given to me. And t lands in the first step of the filtration, so this extends to not from all power sequence. And now then I claim that there is a canonical choice of a k infinity double brackets t module here, which is on which the Galois group still acts. Right? And so there is a canonical map backwards, which is just a projection to the zero created piece, and similarly here. And now RH plus of V, it's a free k infinity double bracket C module of the correct ring. Oh yeah, this is invariance on beta 1 plus. Yeah, so maybe this would be a better. So invariance on C were the completion of k infinity hat. Sorry, the completion of k infinity, and then I claim that this gadget is simply is similarly has a filtration whose associated gradients are Tate twists of these in there. Okay. So this is a free module over this ring of rank equal to the dimension. Okay. But now, so the interesting data about my representation is contained in how the Galois group acts here. Right? Now, what kind of action is this? How does it interact with the structure of a module over this ring? So, by a similar computation, since I know how the Galois group acts on T, well, so the Galois group acts on this. Well, the Galois group acts on this T via its atomic character, and so I can similarly take the derivative of this action gamma k, and I can define an operator phi acting on this RH plus by this same derivative formula, and how will it interact with k infinity double brackets of T module structure? Well, how does it? Let me kind of run this procedure first for the trivial representation instead of phi, so where I just take invariance in beta 1 plus under hk, and then my decompletion is just k infinity double brackets of T itself. So I just look at the gamma k action on this ring, and I derive it. So the action is compatible with the action of phi on this base ring. And here, well, since it was a derivation of an action by automorphism of the ring, this phi acts as a derivation of this ring, and since phi of T, since my Galois group acts on T by the first part of the economic character, phi of T is T, and since the Galois group was acting for a finite quotient in any element of k infinity, the action of k infinity is trivial. But now if I have a derivation with these two properties, it means that phi here is just derivation with respect to T times T. Right? Because the derivation, k infinity linear derivation is determined by its effect on T. Okay. So we've constructed a map and an dimorphism of this module such that phi of a product of an element in the base ring and an element of the module is not quite linear, but rather the formula is that this Leibniz rule. Okay. So I claim that this computation is a consequence of how the Galois group acts on beta 1 plus. And so finally, I've reduced my desired module with a connection on the punctured disk. So, or rather, a specific lattice on a non-punctured disk. So I can equip RH plus with a connection, so which will just be T inverse M phi. And now notice that this satisfies the usual Leibniz rule. Sorry, let me write it more carefully. So connection should be a map from RH plus of V to RH plus of V tensor my module of logarithmic differentials. And the connection will be recovered from this phi as phi tensor dt over t. And the law which I noticed here, it will get translated into the Leibniz rule of the connection. And since I divided by t, it will be the usual Leibniz rule. Right? So the upshot is that we produced, starting with an arbitrary Galois representation, a module over this ring with a logarithmic connection. Are there any questions about this?
Why would always want to work with dt over t instead of dt?
Maybe so I should say that I'm not particularly attached to any, if you like, all of this is linear algebra. It's how we're trying to repackage the action of group ZP cross. For some of the things which I want to do, is for me it was psychologically easier to think about connections rather than T connections.
Sorry, question. Why did you write invariance of HK on the product V tensor Liu-Zhu plus as this tensor product of HK invariance Liu-Zhu plus?
Right, so it's a non-trivial step, but I'm saying that here it's not more non-trivial than over here. So I can construct this decompletion iteratively. So first, I would instead do this for quotients of beta 1 plus by a finite power of t. And there, the analogous thing would also be characterized as the maximal finite dimensional k infinity submodule in which the Galois group acts. Then I would take the inverse of it. So now, how does this look like in examples? So example, if again, V was the power of a cyclotomic character, let me not redo it completely, but really by a similar computation to what we did here, we would arrive at the fact that phi multiplies a basis of, so RH plus of V would be just a free module of rank 1. And phi multiplies the basis element by A. And so, but now since it's not a linear endomorphism, but it satisfies the derivation rule, the ultimate formula for phi and therefore for the connection will be the de Rham differential plus A times dt over t. And now I can finally fulfill my promise of using this to figure out how to compute functor de Rham of these representations. So let me do this here. So in general, if I'm interested in computing the functor de Rham of my representation, at least if I allow myself to extend scalars to k infinity, it's expressed in terms of this RH plus by inverting t in the RH plus and taking the kernel of this connection. Or rather, in other words, flat sections. So, well, why is that? So inverting t simply corresponds to the fact that here instead of beta Rham plus, we would take all of beta Rham. And now, if I'm taking elements killed by connection, it's the same as elements killed by phi. So these are not quite gamma stable elements, but rather you're killed by phi if and only if gamma acts on you through a finite quotient. So this would formally pick out elements in here which are stabilized by, so in which the Galois group acts on a finite quotient, but by a similar trick as what we did yesterday, I think, since beta Rham plus contains k bar. This is literally the same as taking invariance just for the Galois group. Right. This is not the crucial point here. But now, you can notice that in the example of this economic character, so I know that, well, in general, it means that my representation of V is the RAM if and only if this module of a flat connection is spanned by flat sections. So as a module, as a vector space over this field spanned by flat sections. And in the case of a chi-cyclotomic of A, we see that this is the RAM if and only if the module K infinity of T with the connection which is D plus A times dt over T. Well, it's one-dimensional, so it's spanned by flat sections if and only if it has at least one non-zero flat section. Right, and now this is a pleasant computation, but this differential equation has algebraic solutions. Sorry, has a solution in this Laurent power series ring, if and only if, well, not quite algebraic, but in this ring, if and only if A was an integer. Okay. And so this is consistent with the claim that I made yesterday, that this is determinate if and only if A is a cyclotomic character. Sorry, if and only if it's an integral power of a cyclotomic character. And but now this RH plus, it records some information about an arbitrary representation, even if it's not the RAM. So, right, I spent a lot of time on setting up this machinery, but now this was all kind of, it will all be interesting and hopefully worth it when we'll be trying to study the relative case. So before I move to the relative case, are there any questions about what I said? Okay.
So the isomorphism after in general, you're taking point variance.
Oh, sorry, thanks. It's just I'm extending scalars. So this is a K vector space, and I tensor it with K infinity. Okay. So let's finally discuss the relative case. So now my X will be a smooth variety over K. And I'm interested in local systems. And as I announced, our first goal will be for the purposes of not spending infinite amount of time on this, I will not define this very thoroughly, but I'll rather say what ingredients go into the definition. But we'll define a functor which is the analog of d de Rham from local systems to vector bundles with a flat connection. Say, I'll note them by E on X itself. Equal to a Griffiths transversal filtration. So, as I said yesterday, I think the filtration should be by sub-bundles. So all the quotients are locally free, and it's the connection displaces it by at most 1 degree. Right? And this was one functor which we'll try to construct. But now, what will be the? It will satisfy certain properties which, on the surface, will sound very natural, but in a second we'll see that if you trust those natural properties, there are some striking consequences about the situation. So if my X was a point, then this is really what we've been doing all along. So properties, if X is a point, then local systems are just representations of the Galois group, and this is this period ring construction. Now, the second property, which seems innocent, but this will have a lot of interesting consequences, is that this construction, I said in general, unfortunately, this, as we already saw, this functor in general loses some information, so some local systems get sent to 0. But this is at least functorial in the variety. So if I have any map between smooth varieties, so y and x are both smooth, the map is arbitrary. And if I had a local system on X, then if I first calculated d derivative on X and then pulled back this vector bundle of flat connection, it would be the same as first pulling back the local system and then calculating d derivative on this point. Right? This is a function. So if we believe these statements, then we immediately get the following surprising theorem. Of Liu and Zhu. So, as I said, in general, there are many Gaussian representations which are not de Rham, right? We see that here in this family parameterized by A, most of them are not de Rham. But suppose I had a variety over X over K which was connected. And suppose I had a local system. And suppose it was known to me that there exists a point, say a K point of this variety, such that if I take the stalk of that local system at this point, so or in other words, I pull back my local system from along a morphism spectrum of K to X, to just get a local system on spectrum of K, which is just a Gaussian representation. So it's just a vector space with an action of the Gaussian curve. Suppose that this was the Rham. If there exists at least one point such that this action is de Rham, then the stalk at every point is de Rham. And even it doesn't have to be a K point, I could pass to a finite extension. So for any even finite field extension of K, and for any L value point of X, the stalk of this local system at Y is de Rham. So this tells you, let's just zoom out, let's contemplate this. So it tells you so if you think of a local system as of some variation of Gaussian representations across the points of the base variety, it tells you that, say, if one stalk was de Rham, then non-de Rham representations cannot appear at all in other stalks. So, well, this particular concept is not so impressive, but in particular there cannot be a local system whose fiber at one point is an integral powerless economic character, at another point it's a non-integral powerless economic character. I mean, that you can just prove by hand, but... right? So why is it true? I claim that it's formal from these properties. Well, because I claimed that there's a single vector bundle which interpolates between the result of applying d de Rham to all the stalks. Well, because the fact that Lx is de Rham is equivalent to saying that the dimension of d de Rham of Lx is equal to the dimension of the Gaussian representation itself. But I'm saying that this vector space was in fact the stalk of a vector bundle d de Rham of L at the point x. So it's in fact the rank of the vector bundle d de Rham of the whole local system as a vector bundle. But then this is of course the rank of the local system. Okay. So if of course if it's one stalk the d de Rham has the right dimension, it means that this whole vector bundle has the correct rank, equal to the rank of the whole of the local system. But then applying this logic in reverse for any other point y, and well, using that, using that after d de Rham commutes with finite field extensions, I get that all the other points also have to be. So it's a natural sounding statement. There's a single vector bundle interpolating d de Rhams at arbitrary points, but it has this non-trivial sounding consequence. And in fact, if we think about it, it could have been, you probably believe from kind of general experience that there should be some object interpolating between d de Rhams of different fibers of the family, but I'm saying it's really a vector bundle. And today I'll try to explain why this is really a vector bundle which forces this line forward. Okay. Any questions about this?
Sorry, at this moment, do we have a notion of drum local system?
Ah, very good. Very good question. I almost forgot about this. Okay. So let me make a definition. That a local system will be called Durand. If this vector bundle has the correct rank. Okay, so well, maybe my variety. If my variety is disconnected, it means that this holds on every component. But this, if you grant these properties of the function d it shows that this is equivalent to demanding that the stock of the local system at just a single point is a drum representation. Thank you. But I haven't told you the definition of d right? So let me do the following. Let me rather write down how the actual p-adic Riemann, well, what I actually want to call p-adic Riemann-Hilbert will look like. P-adic Riemann-Hilbert function will look like. It will be a relative analog of this RH plus, and then I'll say how this d-dram is recovered from this function. But it's at least psychologically easier to first figure out what's the relative version of the functor h, which I already erased. And now I can finally disclose what h stands for. So the claim, so this is p-adic Simpson and p-adic Riemann-Hilbert functors. So I claim that there is a functor h from, again, QP local systems. On X, to the following piece of data, and this is supposed to be an interpolation between these h's of different stocks. It will be a functor to Higgs bundles. Let me call them M, since I already reserved a vector bundle. Again, on this X k infinity, because for points I was getting k infinity vector spaces. And there is a Higgs field in the very same sense as in Daniel's law. So it's a linear map from M to M times 0 equal n. But now, crucially, there's additional data, and it kind of reflects. So let me write it down what it is. So it's an endomorphism of this bundle. So just a bona fide linear endomorphism. And how does it interact with the Higgs field? It doesn't quite compute with the Higgs field, but it has the following relation. So if I apply theta commute with phi, is the same as theta minus 1 composed phi. So it doesn't quite commute with theta, but rather there's the following strange relation. And I'll try to explain where this relation comes from. And so the key properties are that pointwise, the stock of this bundle is just this functor h. My notation for local systems was L. So if I took the stock of a local system at X and I apply this functor h, which I already defined, and here this phi is simply this operator which I already defined. And so it's really a consequence of what I said here is that this construction h preserves rank. Okay. So as opposed to the functor d-drum, it does not kill any local system. And this once we've defined these functors for all the for just representations of the Galois group, it's maybe natural to expect that they in some sense vary, if my representations vary in a local system. But now I'm saying that this variation is controlled, is restrained by this Higgs field, which interacts with this phi in a funny way. So let's first of all say why we could expect such a relation. And like, if you already know that there's supposed to be some Higgs-like construction, and there's supposed to be this operator phi, how could they interact? Well, let's consider that our main motivating examples of local systems of geometric origin. So, so an example is if L was cohomology of some smooth proper family of varieties, then what should be H of this local system? Well, I think I already raised it, but I said at the beginning that at every point, if I apply this functor H to homology of a smooth proper variety, this is supposed to decompose as direct sum of Hodge cohomology groups. And the same just will hold in families. And this is completely parallel to how the usual the complex Simpson correspondence works, as Daniel described in his lecture. This will be a direct sum of relative Hodge cohomology sheaves. But again, by the nature of the setup, I always work over T infinity. So this is somewhere right. Now, what is the Higgs field on this? Well, again, the claim is that the Higgs field is what you expect from a complex story. So the Higgs field, it doesn't quite respect this grading, but rather it shifts it down by 1. So sorry, this is y over x. And this is what I think Elon was calling the copying of the Kadar-Spencer class, or it's also just the associated gradient of the Gauss-Manin connection on the relative Durand cohomology. And this is the same Higgs field as what appeared in Daniel's talk. But now I also told you how this operator phi acts on Stokes of this bundle. And we saw that on the I graded piece, phi was acting by minus I. And so this confirms this funny relation between theta, so between phi and theta, which is that theta goes from the eigenspace for phi with value minus I to the eigenspace for phi with value minus I plus 1, which is exactly saying that this holds. Okay. But now sorry, are there any questions about this example? Okay. But now what this buys us is that I actually claim that this relation places a very strong restrictions on what theta can be. It's a very pleasant computation that the remark is that this relation between theta and phi implies that the Higgs field is nilpotent. So in other words, as Daniel said, that this bundle has a filtration such that on the associated gradient theta is by 0, and well, since this is right. And this follows, it's essentially the analogous computation to what Daniel mentioned in his talk, but it's kind of a logarithmic version of that. So this implies that my bundle M with its Higgs field theta is isomorphic to the same bundle with rescaled field theta. Or some, which is not a real unity. And so, as Daniel mentioned, this forces the Higgs field to be no-limit, and the same happens here. So, the upshot of this is that this action of phi, which was coming from an action of the Galois group, it places restrictions on the Higgs field, and so the Higgs field at least shares some properties of Higgs bundles which come from variations of Hoche structures. All right. Are there any questions about this iteration?
If X is over CP, you get the Higgs bundle but not the phi.
Exactly. And then there are no restrictions. Well, sorry.
And it's not necessarily no in that case.
Exactly.
Galactic is no.
I mean, when I say that, when I agree with you that I get it, there is a whole story of p-adic Simpson correspondence, which, right, but within that story, when its assumptions are satisfied, then you do get it. Right. Now, any other questions? So let me say what p-adic Riemann-Hilbert is, and this will sort of be an additional structure which will place even stronger restrictions on how this p-adic Simpson correspondence can look like. So the claim is that these functors RH plus, which I mentioned, they're also interpolated in the following way. So there is a functor RH plus from QP local systems. To now, well, it's supposed to be some piece of structure which fiber-wise gives me modules over these Taylor series rings. And one way, so my Taylor series ring was complete with respect to the p-adic topology. So one way to work precisely with this notion is to work with formal schemes, but let me just give an ad hoc way of thinking about this. So let me introduce a gadget which I'll call xk infinity double brackets t. You can either think of this as a formal scheme, which is a trivial thickening of xk infinity in one direction, or you can also just think of it, it's a different, mathematically different thing, but for my purposes it will be equivalent. You can think of it as a locally ringed space whose underlying topological space is just that scheme, but the structure sheaf, I would join the formal power series variable to the structure sheaf. Okay? And so the notion of a vector bundle in such a gadget will just be a locally free, will be a sheaf on this, which is a locally free modular vector. Okay? So it will be vector bundles on this funny xk infinity adjoined by variable. So geometrically, you should think of this as a kind of formal, as a formal disk times xk infinity, non-punctured cube, which I'll call E. And now this will be, oh, there are kind of two ways of thinking about this. One is maybe more analogous to what I was doing over a point. The other, let me give you both of them. So it will be equipped with a connection, but now it will really be a connection both in the geometric direction along x, as in the usual Riemann-Hilbert functor, and as in the situation of our point, there will be a connection in the t direction. So it will be a map from E to E tensor the following. So it will not quite be a regular connection, but I'll allow poles, and in fact, this will not be quite the thing. It will not be logarithmic connection with respect to t, but I'll allow arbitrary poles in the t direction. So I can go to the differential forms with respect to which I'll consider the notion of the connection will be. Okay, let me give myself more space because it's the threshold data. So with connection, nabla, and nabla will be a map from E to E tensor sheaf of differential forms on xk infinity. Well, which now I just this is just the it's a bundle whose rank is the same as the dimension of the variety. But now, well, I just pull it back to this tube. So I just formally join to the power series variable. And also, I allow differentials in the t direction. So let me just write this as structure sheaf, but spanned by the symbol dt. Okay, and I allow poles in the t direction for both of these geometric and arithmetic part of the connection. Right, so it's kind of a mouthful, but and it satisfies Leibniz rule in the sense you imagine, because you know how to take derivatives of sections of the structure sheaf. So on x you take the usual derivatives, and on t you also take the usual derivative. Derivative of t is 1. And so with a flat connection. Satisfying Leibniz rule.
So it's still just a simple pole.
Yes, just right. So let's. I said it was a kind of a scary looking piece of data. Let's consider our favorite example of a local system of geometric function. So how does it look like? So if L was again cohomology of a family of varieties, then RH plus of L, it will look as follows. It will be the Rees construction applied to the Hodge filtration on the associated bundle of Durand cohomology. So it will be a sum taken inside just the relative bundle of Durand cohomology. So now this is just a vector bundle on x over k, but I can base change it to OXK infinity adjoin t, and let me even invert t here. So this is kind of a vector. This is a vector bundle over a punctured trivial punctured neighborhood of xk infinity. But now inside here, I'll choose a particular t lattice, and this lattice will be the following. It will be, as I said, this Rees construction. So it will be a sum of ith pieces of the Hodge filtration, which is some sub-bundle of this vector bundle. But now if I'm in the ith piece in the first summon, then I allow poles in T in the second summon. So here I'd consider a power series with poles of order at most. And now I take just a span of these subbundles. And the connection here is, well, it's just the direct sum of the Gauss-Manin connection, what's induced from here. Or rather, I should just say the tangent product. The Gauss-Manin connection. And just the usual derivation here. Now you can see that when I derive this, so when I derive t to the power minus I get some multiple of t to the power minus I minus 1. So d displaces the function by at most 1 power of t, and WGM also sends this to f I minus 1 at worst because of the Griffith terms. Right? Now, how does this connect with this Simpson's functor h? So, see, what does it take to give a connection on a on a bundle on a space which really looks like a direct product, right? It's x times the formal disk. So I can just decompose my nabla into, so it's a map into a direct sum of two things. So I can just decompose it as two components. So I can write nabla as a sum of its geometric part and its arithmetic part. And hopefully it's clear from the indentation that I just mean that nabla geometric is the composition of nabla with the projection onto this summon, and nabla arithmetic is the projection onto that summon. And since the connection is flat, these two summons, they have to commute with each other. And if I like, I can rather think of this connection nabla as the pair of the data of nabla geometric and the data of nabla arithmetic. And nabla arithmetic I can rewrite in possibly more familiar terms. So this target category of RH plus is equivalent to the following data. It's bundles on the same space. but this time only equal to a connection in the geometric direction. Right, there are no differentials in t direction, but well, there is t in coefficients. And now the Snubble arithmetic is expressed in terms of the operator phi, and this is the phi from before, which is now an endomorphism of E without any poles, which is OXK infinity linear, and but it's not T linear, so it satisfies the same condition as before. So f of Tm is, sorry, phi of Tm is T times phi of m plus m. So, and the correspondence between these two things is that phi is recovered as T times Snubble arithmetic. And this is just a restatement of the Leibniz rule from Snubble arithmetic. And well, the flatness, the crucial flatness condition of Snubble is expressed in the fact that now Snubble geometry commutes with phi. Okay. Right. And now, having said this, I can say how RH is related to H. So, property is that, put it here, is that H of any local system is recovered from RH of it by modding out by T. And here, the Higgs field, that's just the graded piece of the connection, of the geometric part of the connection. But, so what exactly I mean by this, let me say this more carefully. So on RH plus, I had this geometric connection which didn't quite respect RH plus, right? But rather it introduced a simple pole in the t direction. But now if I mod it out by t, since, well, it will give me a well-defined map from the mod t reduction of E to the mod t reduction of E, tensor one forms, and now, well, t would be gone because I mod it out by t. And this would be exactly the Higgs field. And phi would be this phi mod t, which is just t times Snubble arithmetic mod t. And this relation between theta and phi would arise from this commutation between phi and null. Right? So this is all kind of a little linear algebra, which takes some getting used to. But what I'm trying to emphasize is maybe this. Just somehow the relations between, it's kind of the way, so that the key point is that point-wise we have this arithmetic information of phi, and the way it varies, so there is either Higgs field of the connection which are responsible for the variation, and they interact in this twisted way. Let me maybe, so as not to say something completely incomprehensible, let me call today for today, and tomorrow I'll continue with some applications.
So in a classical setting, this H is like a bijection. To get H to be a bijection, we need to introduce like stability condition on Higgs models. Is this understood in IAS?
Definitely not, but somehow here it's even worse in that, so there are kind of two stories, I think, what Christian pointed out, is that there is the kind of a closer analog of classical Simpson correspondence, or p-adics, would be if I worked with varieties not over a discretely valued field where there's an interesting Galois group, but rather over an algebraically closed complete field, such as CP. And there's been recently a lot of progress, especially by Ben Hoyer, where there is a very good version of Simpson correspondence, which is really an equivalence of categories. It's still not quite, it's not yet clear if there is an equivalence between category of local systems and category of Higgs bundles of certain kind. So it's not clear if this is exactly the stability condition. But what I'm doing here, it's there's a crucial additional Galois action. And so this functor is really far from equivalence, but what I'm trying to emphasize, so the whole point of this discussion is that this Gauss equivariance introduces for me this additional operator phi, which puts a lot of restrictions on this Higgs. Yeah, but over CP it's a very interesting story. That there are many things that are not completely understood. Okay.
Just the setup over here
Yeah.
can formally imply the obfuscate weights for the constant.
Exactly, this was going to be my next article idea. It's a theorem of quantity Schmidt. I mean, if you have a proper variety, you could also cheat and use that this phi would be an endomorphism, so its conditions of the characteristic alone will be constant. It's actually a purely local statement.
Can you give a, so is it possible to, it's probably possible, but I'm just wondering if I've done it. Namely, you use your new Riemann-Hilbert functor to give a proof of the fact that the round implies potential unstable.
Well, sorry, is there any proof of this fact so far?
No, I mean, you even just for Gauss stations.
Not that I know of. I think somehow, well, this functor RH plus, its purpose, I mean, as we saw, right, it really remembers very little. It's kind of, on the category of de Rham representations, it ultimately remembers only as much as d de Rham itself with its filtration. So, I don't think maybe a more helpful answer to your question is that the first proof of this due to Berger, it used exactly similar gymnastics with associating together representations modules with connection over some rings. But this was more, what Berger was doing was closer to phi gamma modules, Bergkissen modules. And here I'm going to do a very small part of it, if you like, around the de Rham form. So maybe the answer is that this perspective is helpful for proving this thing. And that's how the classical proof, the first proof goes.
Are you gonna say how to make Nicolas or?
Well, given the timing, unlikely, but I have a prepared sentence which is supposed to explain it completely, but does someone really have the right to not be satisfied?
Any other questions? Okay. Some coffee left over from upstairs over there. In case you want
I guess once you have this, the local constants, the quantitative weights, it's just like the constants